Greetings and salutations, everybody. Beautiful day for a webinar. And we've got one of our stars presenting today in Sean Quilty. But before I talk about how wonderful Sean is, I'll give people a chance to come through the virtual turnstiles. But yeah, look, just a reminder, folks, we're back, basically. We're back, baby. I think it's the third year we've been doing the now award-winning Stormwater Fundamentals series. I've realised I've still got that as 2025. That should be 2026. Shows you how much QA check we do on these slides. But look, this is the schedule, and actually, there's actually a new one we actually haven't even promoted just yet. And there's actually now 13 webinars in this year's series. I'm going to change this because it's annoying me. Pedantic engineer. It should be 2026. Bang.
I feel you, Brad. I do the exact same thing. I say, hold on, everyone.
I'm living in the past, man. But we're actually looking to add in a couple of more webinars as well. We're just looking to finalize the details. But in summary, we're bringing you all the good stuff this year in terms of trying to improve and share knowledge across the industry. But yeah, the one we haven't previously promoted was this: how much does bioretention cost, which will be presented by Harry and Mark from Optimal Stormwater. But yeah, we've got Sean doing 3 more webinars this year. We're spacing Sean's prezos out throughout the year because people are just overwhelmed with the amount of energy he brings. So we're spreading it over the 12 months.
I think it's more they're overwhelmed with the equations, Brad. Let's be honest. There's too much, Sean. Just slow it down.
There's not many shortage of equations and energy because we've got Murray Powell coming in for a couple, I think 3, I think. Obviously, Harry from Optimal as well, Daniel Ryder, myself will make a guest appearance a couple of times. And we've got some cool cats from the University of New South Wales as well coming along for the microplastics one. So stay tuned. If you're keen to, if you haven't already registered, feel free to jump on the oceanprotect.com.au/events page. And if you're not already, please subscribe to our newsletter because that's how we plug these things. But yeah, we're here to talk about road flow design, which is, I'm excited. But look, before we do, I mentioned this report. This is hot off the press, literally released today. It's a full disclosure. It was a study that Ocean Protect funded, but it was done by Optimal Stormwater, and it basically provides a summary of lifecycle costing information for bioretention systems. So the big question mark I see in our industry is how much does bioretention cost? Because we've been using lifecycle cost data that's at least 11 years old. And as Optimal has shown, it's very much inaccurate relative to present cost data. So that's a couple of snippets from the report. But in summary, conventional bioretention systems are actually more expensive than what has previously been predicted using previously available and publicly available lifecycle cost data. So in summary, Harry got cost data from a bunch of councils, bunch of private groups for about 78 bioretention systems, and established unit rates for these things as well. But if you're keen to find out more, just download the report from the Ocean Protect website, and it is available at that link you can see at the bottom there. We're going to have a webinar to talk all about it as well. Speaking of talking, who doesn't love a good podcast? And Sean has even made a guest appearance. Ratings went through the roof. I'm sure it wasn't just him listening to himself. But we've got a couple of crackers in recent times. Our very own Justine Barrett from CSIRO talking about one of the chapters of her PhD, basically talking about GPTs. And if you love stormwater, gee whiz, you're going to love that one. We had obviously Cal Glanznig before Justine a few weeks prior. A 25-year-old Sutherland Shire Council councillor and filmmaker. So absolute cracker of a podcast, and we'll be releasing a podcast for this year in probably in a couple of months' time. But before we dive into Sean's prezo, just a reminder, folks, if you do have any questions for Sean, please put them in the Q&A panel. The slides and Sean's recording with his dulcet tones will be made available on the website. Just give us a day or two. And CPD forms. We've streamlined this process, I think, pretty well nowadays. But if you haven't received your CPD within 1 week of attending, please just email us. And I'm going to, Sean, if you want to take over, but whilst you do that, I'm going to embarrass you by saying how wonderful you are. It's a pretty short speech. But
Oh,
for people who
geez.
don't know Sean, he's a chartered civil engineer and he's got 20 years experience. So that's there's a few more extra grey streaks in his hair.
Yeah.
I used to think they was just sort of dyed, Sean, but maybe it's a natural thing. It's working for you though. And he's the co-founder of Quilty Engineering Hub. And these guys are just legends, basically. You know, they are carrying the mantle for capacity building in across many for stormwater professionals everywhere. So they do awesome stuff. If you haven't already heard Sean speak or learn from him, oh, you're in for a treat, I tell you. And he's a two-time nominee of Engineers Australia of the Year for Queensland. Two-time crashing and burning, so he didn't win. Is that right, Sean?
That's right. I just wanted to get in amongst the great people of Queensland. That was enough for me. I
Very
was sitting
good.
on the corner.
Look, I think you're Rob, just between you and me. But yeah, look, he's obviously spent many, many years capacity building, particularly at TAFE as well, where he's um, inspired the next generation of storm professionals. So look, I'll pass you over to Sean. Can you share your slides, okay, Sean?
Yep. Hopefully everyone can see that. Just let me know
Awesome.
if you can't. Beautiful.
Hang on. Actually, no, I can't.
Oh no.
You-
Let me make sure that share's working.
Yeah.
Try that again.
So I'll leave you in the tender care. And thank you everyone for dialing in today. Your attendance is appreciated. Another super popular webinar. I think we've got 550 registrations. So no pressure, Sean. Uh,
Never. Brad, just check on your end.
Hang on. I'll stop sharing. Yeah, maybe that might be blocking. But here we go. Okay, now I can. Okay, if you want to press start.
Hit share again.
Yeah, that should be okay now. Actually, I can now see your slides. Maybe I was blocking
Yep,
you somehow.
that's right. That look all right now?
Looks good to me. If there's any
Beautiful.
dramas in the chat, just let us know.
Excellent.
And we'll
Thanks, Brad.
thank you, Sean.
The $100 check for that intro is on the way too. Thank you.
Awesome.
Welcome everyone. We'll get stuck into it. All right. So welcome to 2026. Really, I'm pretty pumped for the year. I think it's going to be a pretty exciting year. Hopefully, full of growth and professional development and learning something new. So today, hopefully, I'll help you on that journey. So we're going to look at road flow design. From a stormwater perspective, this is something that everyone basically has to do if they're doing any sort of pit and pipe design or any sort of road design, even just geometric road design, they should be able to do this as well. So if this does sound new or something that maybe you haven't done or your team hasn't really focused too much on, hopefully you'll be able to go back to the team and spread the knowledge a bit and get people starting to sort of talk about this and discuss as well. So we're going to talk about road flow design. I'll run through a little bit of theory, a little bit of practical sort of knowledge, and then at the end I've got a bit of a worked example where we use a very common equation to work out how much stormwater will actually be able to flow down a road. So super useful equation. And then obviously once you've got that, take this today and then tomorrow you could probably create your own spreadsheets and automate all those sorts of processes and make your design life hopefully a little bit easier. So we'll get stuck into it. First, we're just going to touch on road flow and urban drainage systems. Basically what I'm trying to tell you, I suppose, what we're talking about. We'll put in some real tangible sort of ways so we understand what we're looking at and we can visualize it. So when we're looking at road flow, today's talk is focused on urban drainage systems because we've got curb and channel and a road type formation. So that's what we're going to focus on. But the reason why the road flow or how much water can actually run down a road, the reason why it's so important is because the roads actually act as part of the stormwater drainage system. Now, I look at roads and that's the first thing that I see because I'm a bit of a stormwater nerd myself. I'll just see a big open channel. I don't actually see a road for traffic and cars and everything else. That's sort of secondary to me. The first thing I think about is flooding and how much water that can actually convey. And where along those roads is there a problem where the water just sits, where it's in a sag. So hopefully after this, you might look at roads a little bit differently as well. So the Australian Rainfall and Runoff, which is our national kind of guideline, I suppose, for stormwater, the stormwater Bible, if you like, it recognises that roads basically are acting as overland flow paths. And so that's a bit of a mindset shift that you've got to take when you start to get into stormwater engineering and stormwater design. So these road flows, it's an intentional component of the major stormwater drainage system. So it's not just about pits and pipes and head walls going out into a creek. The actual road itself forms a very big part of that. So with this, when you get into design, you've got to make sure that you start to focus not just on the geometry, but also think about the safety and the risk. Because when we've got roads, we know we have vehicles and we have pedestrians. So there's a few things that you'll see that we have to try to tie in and balance when it comes to design. So when we're looking at road design, it's important to remember that exceedance is expected. So when I say exceedance, that means when the flows that are going through our road, it exceeds the minor system capacity. And we'll talk about major and minor systems shortly as well. But just remember, our roads and our more importantly, our pits and pipes, they're designed to exceed. They're designed to be overwhelmed or overcapacity and surcharge and spill out. That's how a good civil designer or civil engineer will actually design their systems. So AR&R, again, they state that exceedance is expected and it's unavoidable. So we know when it comes to stormwater frequency, so how often you're going to get these sort of storms or how rare, how intense they might be, we're never able to construct or engineer a pipe or a road to convey the stormwater all of the time. There's always going to be some events that will exceed our design expectations. And that's how we try to build that into our design as well. So then, if this is true and exceedance is expected and we can't avoid it, we know the roads are going to flood, our design focus then shifts from prevention to consequence management. And this is something that I've sort of believed for many years now. When it comes to stormwater, maybe 30, 40 years ago, it was all about looking up, sort of design tables and charts, and you can kind of pinpoint exactly what the storm's going to do. Whereas we know it's much more unpredictable. And especially when we start looking at the climate change impacts that we're feeling already and going into the future. We've got a webinar poll there too. If you get a chance,
Sean,
click through that.
Obviously,
Yeah, no, that's
first
right.
time doing this. Got to launch the poll.
That's all good. Don't even worry. No, you guys flick through it if you like. Definitely, I'll encourage everyone to jump into that poll. We'll always share the results as well, which is really good to just give you a bit of insight. So when you've got the answers, you can say, well, half the people thought this, half the people thought that. Now, it's all anonymous. No one knows who voted for what. You just get the overall sort of percentages, but it's just really good insight. So encourage everyone online, if you've got a few minutes, just tick away as we go through today. So when we look at the design, it's all about prevention and not consequence management. So we're going away from the old school thinking of a Q100 storm is exactly this with this exact freeboard, and now we're getting into more risk management and risk sort of identification and mitigation. So we're saying, well, there's a bit of a spectrum now of what that storm might look like. It's not as clear cut as we once designed to. So that's where you've really got to start thinking about risk and safety, and just thinking about that sort of, that spectrum. How bad can it actually get? So again, roads commonly convey exceedance flows. So as soon as that minor system is overwhelmed, the road is designed to then push the rest of that water that exceeds that design. So when we start looking at roads, and again, I think everyone will look at roads a little bit differently now, but in any new road that's now designed, in the last sort of 50 years, those roads are designed to be an overland flow path, particularly in urban environments. It's just a great big, wide, very shallow channel, essentially. And so AR&R identifies this. They know that overland flow paths are critical infrastructure now when it comes to stormwater. So it's not just the pits and pipes. And in fact, I'd go as far to say the pit and pipe drainage is just a very small part of the design, and you shouldn't even really rely on that, to be honest. You should be looking at the major systems, these overland flow paths, your road design. I would personally rather spend 80% of my time designing that than the other way and focusing on pit and pipe design for most of your design. And unfortunately, in the industry, the people that I work with, me as well, coming through, I used to focus a lot of time on pit and pipe design, and whether it was 12D or now if it's Civil 3D or Civil Site Design, I'd spend hours and hours getting your pit and pipes just perfectly functioning. And then I'd have like a very small time, I go, oh yeah, I better check that road flow. It should be the inverse. You really should look at the road geometry, where your overland flow paths are going, and really be comfortable with that, and then jump into the pit and pipe design. So the roads are really acting as continuous, predictable flow paths. Now, in this little image here, this is an overland flow path map, pretty common in all councils, really. But you can see here, it's a reasonably new estate, which means that all the roads pretty much align with where the overland flow paths are, which is, I think is pretty cool, because I've designed a lot of roads and I've looked at a lot of existing infrastructure, and that's not always the case. But that kind of gives you an idea where it rains, water's coming from all over our lots and houses and parks, and you can see it just starts to accumulate in those roads, and that's what you want. You want that water, that flooding, to actually be conveyed within the road reserve and not affect people's properties and houses. Blocking these flow paths, obviously pretty bad idea, something that we definitely want to avoid at all costs. So that's also something to think about when it comes to designing. Particularly when you get into infill development. So if you've got an urbanized area and it's been around for 70 or 80 years, and then you're putting in a new development right in the middle of it, all of those roads that were built, many, many decades ago, they wouldn't have been designed to our standards, and some of them don't adhere to this rule where roads are an overland flow path, and that becomes a big problem. And you've got to a lot of time, it's not just looking at your site, you've actually got to look at the surrounding infrastructure and see how risky it is and how you're going to mitigate that as well. That's what we're talking about when we say road flow. It's all about the water running down our roads. So when it comes to design, we know that we need to think about safety and what sort of hazards we might encounter. So the most common approach to stormwater design for urban areas is where we look at minor and major drainage systems. Now, we split these up because as engineers, we like to be very, well, to be honest, we're a little bit lazy. We want to spend the minimal amount of time designing these things. And so if we try to design for every single storm, you'll be there for months on end, and you'll just be overwhelmed with the numbers basically that you're going to get, and you've got to filter through. So we try to simplify this by splitting it into a minor system and a major system. So the minor systems are for very frequent storms, so not too intense, the rain, and something that you'd expect to see, every year, every few years. Major storms are where it's once in a lifetime, let's call it, type of a storm, pretty rare sort of a storm, but it does a huge amount of damage because of the intensity of the rain falling. The minor systems consist of underground pipes. So pit and pipe design, that's basically what we put in the ground just for these minor systems, for the very frequent storms that are occurring. And that top image kind of shows you what it sort of looks like. So shallow flows, the roads are pretty much, dry in the sense that water's not running right over the road, and you control a lot of those flows with your pit and pipe. Then when you get into the major flows, we know that the pipe capacity will exceed, because we know exceedance is okay. We're expected to see these pit and pipe systems exceed their capacity. So that flow then transfers to your surface system. So the bottom image there, you can see we get more water. The pit and pipe system becomes overwhelmed. Water will come up to the surface. It'll surcharge. And then you're trying to manage that surface flow. So you still want to make sure that that's safe. The other thing that we've got to think about is how you transition from the pit and pipe system, and then how it actually surcharges, because even that transition is an important design factor that you've got to incorporate as well. You don't want, one single gully pit or manhole blowing its top and then becoming a safety risk. You want it to be a controlled manner that it comes to the surface. And then when you think you've got it all sorted, which is kind of how I learned as well, I thought, oh yeah, I kind of understand this. I've got pit and pipe design, I've got the road flow, we're all good. Here's the design. And then someone tells you that you've got to think about blockage factors and failure scenarios. And all of a sudden you've got to redo a lot of that work and look at a lot of what if sort of scenarios. So blockage factors are super important. because when you have a storm, especially the severe, like the really major storms, you're almost guaranteed to have blockage somewhere in the system. Because when that sort of a storm comes, it's a massive, east low pressure system. It could be a cyclone. We know even here in Brisbane, we get hit with cyclones now. So when that sort of a storm comes, there's a lot of debris, there's fallen trees, there's all sorts of stuff that will block up our pit and pipe systems. So that's something that we've got to think about. And even the roads themselves as well, they become blocked with all sorts of debris. So you've got to think about that when you come to design, especially for the road flow as well. If something blocks, maybe more water is going to come to the surface than you anticipated. And then when it comes to the safety or the hazard that's actually occurring, this is one of the most common metrics that we use, which is the depth velocity metric, or the DV product that we use. And so what it essentially tells us is when you get the flow that's running down your road, it will have a certain depth and it will be traveling at a certain velocity. So when you take that depth and velocity and you times or you multiply those two values together, you get a certain value. And then we use that as a threshold. And we say, well, if it's below a certain threshold, we're going to deem that to be safe. This is a great little diagram out of Australian rainfall and runoff. It kind of explains where that comes from. When you start looking in guidelines like QDM or Austroads or TMR, the road design manual, you'll start to see DV values. And if you come back to this chart, you'll actually be able to see where they got those DV values from. And it's basically just comparing the depth and the velocity of that road flow. All right. So we've got a fair bit of theory, I suppose, in there. And as usual, I'm just going to bombard you with the information, and then we'll have Q&A at the end of this as well. But hopefully you'll be able to take this away and over the next few days have a bit of a think about it, put it in practice, and then go back to the YouTube as well and re-watch it and hopefully start to unpack a lot of these things. But we'll put it into practice now, and we'll see how that sort of that theory or those fundamentals come into play. So when we're estimating approach flow or the road flow, we typically will use the rational method. So in urban environments, we're talking about very small catchments. So each sub-catchment for like a gully pit or for an intersection, they're extremely small, relatively small. So the rational method is more than enough to estimate how much flow will actually be going down. So we use that to estimate our road flow. Now, when it comes to gully pits, so you can see a nice little gully pit on the left here. When we start designing pit and pipe systems, we really need to understand that road flow before it hits the pit. And that's where we start to look at road flow as being the approach flow. What's it actually approaching? What are you trying to analyze? And what is that approach flow? There's some things to think about. So when you do look at approach flows for checking your design, make sure you check the upstream bypass. So there might be gully pits that don't capture all the water and it will actually bypass downstream. And so you've got to make sure that you account for that as well. So this is where the half road capacity concept comes from. So I'm going to pull up an equation soon, and we're going to go through a worked example where I'll actually crunch numbers with you. You'll be able to watch this later on and do the calculations by hand yourself as well. But it's based on a half road capacity concept. So when we look at the road itself, we actually split it in half. So this is talking about a typical two-way crossfall road. We actually look at half road on either side. And there's a few reasons for that, which I'll explain. So the road flow safety check that we use is actually a pretty simplified method. So there's a few, I guess, rounding sort of simplifications that we'll use, and you'll see what that looks like. But it makes it very quick and very easy to assess how much stormwater will actually run through a road. Using this concept, we can estimate the flooded depth, the flooded width, and the velocity of that flow running through that road. We can then compare this against safety limits or thresholds and see if that flow that we're looking at is actually deemed to be safe or unsafe. And that just allows us to basically say, yep, okay, that road is acceptable. We'll keep moving on and go on to our next design step. So each half of the road is analyzed separately. And there's a couple reasons why we do this. Most of the time, your stormwater pits won't always be perfectly opposite each other on the left or the right-hand side of the road, because it's really based on the catchment more so than just geometry or symmetrical sort of design. So that's where you'll analyze the half road on each side separately. There's other design criteria that we look at as well. So it's not just for, say, the approach flow for a gully pit. You might be looking at how much flow is running around a curb return at an intersection. And so you want to analyze just that half of the road or that half profile that goes around the curb return. So that's why we split this into half of a road, not the full road itself. All right, so this is how we calculate it. This is how we work out how much road flow is actually traveling down your road. This is Izzard's equation. It will estimate the half road capacity, and it's pretty much just based on Manning's equation. So if you did a Manning's equation check yourself and you kind of, from first principles did it for the curb portion and the pavement portion, you'll end up basically getting this equation. So this is all about approach flow. Make sure you don't mix it up with inlet capture. So when we use Izzard, it's got nothing to do with pits and pipes. This is purely just the flow running down your road. Something that I have seen a couple times. Some people might confuse that with inlets. It's got nothing to do with that yet. You're just working out how much water is actually approaching a particular point. Once we get that though, and we use Izzard's equation, that's when we can start to look at the inlet sizing, because we know how much water is approaching the inlet, and then we take that Q value and then we'll use that in our inlet design. All right, so we're going to do a worked example where we basically use this equation, and I'll just show you all the different values and how you calculate it. It's pretty simple. There's a few steps, but it's not hard to do. And so hopefully you can follow along. And then, yeah, after the worked example, we'll jump back for Q&A. All right. So this is pretty typical. This is something, if anyone's done any sort of pit and pipe design, this will be standard practice. And you would have done this for pretty much all your gully pits, or at least designed for the worst case, and then just use your best judgment to see where you need to look into it a bit further. So the first thing that you want to do is just identify the point of interest. So where you're actually looking at where that flow is actually going down your road. Where's the point of interest? So in this case, I've picked a typical urban residential sort of area, and I've picked a gully pit. And I've said, all right, well, I want to know how much water is actually going to flow towards that gully pit. Before it hits the gully pit, how much water is actually flowing down that road. So that approach flow, QA, subscript A, that's what we're going to use for our calculations. Now, Izzard's equation that we saw previously, that is calculating the approach flow, that QA value. So once we know our area of interest, we can then use our catchment delineation and our rational method approach. And for those of you that may be long-time listeners, you might recall back from 2024 when we did the webinar series, we did a rational method webinar. So if you need a bit of a refresh, definitely jump online, jump on Ocean Protect's website and look up that old webinar. And I think, apologies already, but I think I went way over time for that one. I think I talked the audience's ears off on that one. So be prepared. There was a lot of content that we covered. So step 2, we look at the approach flow, the point of interest, and then we work out how much water is basically coming down for that catchment. Now we're going to do kind of a similar thing with Izzard's equation, and we're also going to get a Q value, but we want to compare it to this because this is going to tell us what's actually going to be generated by the catchment. And you'll see as we go through this, it's a bit of an iterative approach. You work out your catchment flow, you'll work out Izzard's equation, what the Q value is, and then you'll just keep adjusting your flow depth essentially until those values match. But you'll see how that works here. So for this particular gully pit, I've worked out that there's 0.18 cumex, 0.18 cubic meters a second. That's going to run down towards the gully pit itself. So that's what the catchment is going to generate in a minor storm in this case. So now we look at Izzard's equation, and it looks scary, but I promise you it's not tricky at all. It's a pretty simple equation once you crack it open and you understand what it's talking about. So we look at the different variables that we've got. This one I'm going to just focus on the F parameter here. So this is for a flow correction factor. So I've got a bit of commentary here. I won't go through all of it. You can certainly read it in your own time as well. But you've got a factor of 1. Typically, we don't use that. It's a bit of a, I guess, what's the opposite of conservative design? It's probably a bit skinny on the design. 0.9 is typically what we use in urban settings, especially with curbs with a bit of a layback face. And some councils, it will even sort of specify that as well. I think QDM recommends 0.9 as well. But that's all it is. It's just a bit of a factor that we use to estimate how much flow is going through that road. So once you've got the F value, you then obtain the actual half-road cross-sectional profile. So we need to look at the geometry of the road now, because the width of the road, the crossfall, the longitudinal grade, and also the curb shape, profile, depth, all of that will influence how much water you can actually convey through that road. Because remember, this road, this half road section we're looking at, is essentially just a channel. It's an open channel for stormwater. So here we've got a typical Brisbane City Council urban road. This is a older sort of a subdivision. So you've got really big blocks of land, you've got really wide roads, you've got side parking. So that's the one that we're going to use today. Obviously, if we're looking at a brand new subdivision, you're going to be looking at like 300 square meter blocks. You're going to be sometimes have reduced verges, really narrow streets. So depending on the geometry, it can drastically change how much water you can actually get through your road. And obviously that'll impact your pit pipe design. And then for your major systems, especially in newer subdivisions, it's much harder to design for a new subdivision than it was 30 years ago because you just don't have the space. Anyway, so we've got Brisbane City Council Road here. We've got a typical curb. We've got a 2.5% crossfall. So once you get your road design, your cross-sectional profile, we can then continue on with Izzard's equation. Now, this is for an existing road, for an existing subdivision. So you can use this equation to assess how much flow might be coming down in a certain particular point, maybe before you start discharging into an existing pit. Or you can use this for proposed works. So you might have your design in 12D, or maybe another designer has given you the 12D model, and then you need to do a bit of a stormwater check. This is where you'll be able to very quickly crunch some numbers, pen and paper, and then you can see what sort of road flows you're looking at. So looking at a few more parameters that we've got here as well. Our Z values and N values, and the subscript G is for your gutter. So we look at the ZG value is basically just telling you what that sort of slope is for the curb tray. So we calculate that. And again, I won't go through every single little intricate detail in these equations. I'll let you sort of come back to it because I'm just conscious of time. But essentially, we just find out what that batter slope is for the curb. So we've got a ZG value, calculated that. Our Manning's roughness. So typically you're going to have concrete and asphalt for your urban road. So we just use 0.013 or 0.012 sometimes for concrete. So once we've got that for the gutter, the ZG and the NG, we do the same thing for the pavement. So we work out what our slope or our batter is, our crossfall for the road is. And then we also look at the N value, the roughness value for our road as well. While you're there, it'll be handy for the calculations as well. If you just take the width of the channel, the width of the half road, and then if you take away the channel width from the half road width, you'll get your pavement width. And those three values will be used in the calculations as well as you crunch those numbers. But you can see here, all it is just looking at the geometry of your road, and also the surface roughness. So once you've got that, you've got most of these parameters we're sort of ticking through. We've also got this S parameter. So this represents the longitudinal grade of your road. So you'll take that value as well. Again, if it's an existing road, you could use survey, or even if you're really stuck, you could use LiDAR just to estimate what sort of road grade you have. If it's a design, you can obtain it from your model, from your Civil 3D or your 12D model, or a designer might be giving you a design to actually check or start incorporating stormwater. You'll be able to get that from road long sections as well. So then we know what the road geometry is doing, the cross-sectional profile is doing, and also the grade. So you can imagine if we start to visualize this as an open channel, we're kind of picturing this in 3D. And then when all this water runs down, you can see how these parameters will obviously have a bit of an effect on how much stormwater can actually get through. All right, so now we just look at these little D values. So we've got DG, DP, and DC. So we're looking at when it floods, when the flow is running down your road, what is the flooded depth at the gutter or the curb invert point? What's the flooded depth at your pavement edge? And what's the flooded depth at the crown of the road? So assuming a two-way crossfall, we need to measure those values. Now, we calculated how much flow would actually be generated towards this point, and you used rational method, and we worked out it was 0.18 cubic meters a second. The problem here is we know how much water is coming down, we know all our road geometry, but we don't know how deep that flooded depth is. So what you have to do here is you need to just guess a flow depth, run through the calculations and work out what that Q value is. So we're going to assume, say, 100 millimeters of flooded depth. We're going to calculate a Q value using Izzard's equation. And then we're going to compare it to the actual Q value, the actual flow rate that's going to come down your road. And if it's almost always, you're going to guess a number and it's not going to be exactly the same. So when you guess that number, if it's maybe the Izzard's value is a bit high, then our flooded depth at 100 mil, maybe it was too much. So we might just reduce that a little bit, crunch numbers again, and until your Izzard's equation Q value is pretty much the same as your rational method Q value, then that's telling you the flooded depth of whatever you calculate, that will equate to your actual approach flow for your catchment. So it is an iterative approach. So you've got to do some design iterations. You bounce back and forth. Hand calculations are great because you'll learn how to use it. The knowledge will sort of stay with you and you'll be able to pick apart designs. But the next step that I would recommend is after today, you know the equation, jump into Excel, create a spreadsheet, and then you can automate this whole calculation part as well. But for now, we're going to adopt a trial flow depth of 100 millimeters. And when we do that, we can then work out what the flow depth will be at our pavement. And we know what the channel depth is because we know the cross-sectional profile. So we can kind of crunch those numbers and just measure off of our cross-sectional area. So once we have those depth values, we continue on. We can also look at the crown depth. And again, I'll just skim through, just looking at time. But it just explains pretty quickly how you can work out that crown depth as well. In this case, the 100 mil depth that we're looking at, it means that that flooded width or the flow, the water surface won't even reach the crown. So the crown depth is going to be 0 in this case. Now, once you've got all those values, we can then come back to the Izzard's equation, substitute all these parameters that you see here on the left, and then we get, using Izzard's equation and using 100 mil flow depth for this particular road, we've got 0.211 cubic meters a second. So when the flood comes down the road and it's flowing at 100 mil depth, it's actually flowing at 0.211 cubic meters a second. So we know that the actual catchment, I'll jump back a little bit, the actual catchment that we've got was 0.18 cubic meters a second. So at 100 mil depth, that will give you 0.21. That's too much. So we need to reduce that flow depth until Izzard's equation calculates Q at 0.18 cubic meters a second. So you'd go through that calculation again, but instead of 100 mil flow depth, we'd use something a little bit less. So luckily I've prepared one for you already. So if you assumed 95 mil, 0.095 meters depth, that Q value using Izzard's equation will give you 0.18 cubic meters a second. So that's telling us this catchment that's going to produce 0.18 cubic meters a second will actually mean that you're going to have water flowing down your road at this particular point at 95 millimeters of depth. That's Izzard's equation pretty much working at that Q value. But we're not finished yet. There's one last thing that we do. We need to check this for safety. So it's one thing to know how much water is going to flow down your road, but the other thing you need to ask yourself is this acceptable? And that's where the depth velocity product that I mentioned earlier, that's where this comes into play. So when you work out this DV value, you then compare it against some maximum thresholds. If it's below it, then you can say that that flow is safe. So again, I won't crunch through all these numbers, but essentially using your cross-sectional profile, and now that you know how deep the flow depth actually is, you'll be able to calculate your area. If we know our area and we know our flow rate, we can use our nice continuity equation. So V equals Q on A, or typically we'd say Q equals V times A. So we rearrange that, we'd work out our velocity. So now we know our flow depth being 95 mil, and we've calculated our velocity. So we multiply those two values, and we get a DV value of 0.161 square meters a second. Now, there's lots of different guidelines out there, obviously going to depend on councils, states, type of infrastructure, but some typical values that you might see. If there's no risk to life, you can get a DV value of up to 0.6 square meters a second. If there is risk to life, you have to bring that down to about 0.4. In this case, we've got a DV of 0.161. So that's less than both of those thresholds. So we can then say that this flow running down this road is actually safe. And that's a relief because this is an existing subdivision, and I'd hate to see my calcs telling me that the road flow down this existing road is actually unsafe, because that wouldn't be a great outcome. So do encourage everyone, in your own time, crunch some of these numbers. If you haven't already got these calcs in your workflow when you're doing designs, or if you're checking as well, if you're working for council and you're getting a lot of development applications and you just want to do a couple quick sanity checks, or even just check some of your own infrastructure where there might be flooding issues, you could use these calculations to see if maybe the road flow is the issue. Of course, I try to make it easier for everyone. Hand calcs are great, but spreadsheets are even better. So there is a road flow design spreadsheet for you if you like. You can get your copy. This is included with the online course that we've got. But also, I'm happy to share it with people if you want to tee up a meeting with your team and your manager and just have a bit of a chat. I'm happy to show them the spreadsheet, just show what sort of stuff that we offer at Quilty Engineering Hub as well. This spreadsheet's pretty useful. You might recognize the format. Qdom, in the back of Qdom, they've got a couple static tables. Well, I basically just generated a similar one where you can punch in your own road geometry, put in your own thresholds, and it will actually give you all your results. And it flags the results as well, like if the flow's over the crown, it'll just give you a bit of a red symbol. If it's beyond the flooded width that you're allowed, it'll give you a red symbol. And if it's beyond the DV values as well, it'll flag that too. So pretty quick, easy lookup tables. A few councils I've helped prepare these as well, where you'll just have them for their typical roads, and you can just have it printed out, and you can do very quick checks on basically any road within your jurisdiction as well. If anyone's interested, obviously always reach out, email, LinkedIn, give me a call, whatever you like, and we can help you out there as well. All right, so that is road flow design. If anyone wants to know any more information, they want to really get down into some some calculations and pull things apart and talk about their own project problems, again, please reach out. We can book a workshop. We can do it online. We can do it in person, and we can help you out as well. But I think that brings us up to the end. So I think we'll jump into Q&A. The poll is still up as well. So if you haven't already, please really encourage you guys just to flick and tick that, just to basically just give us some insight into the industry and see if you guys know all this stuff, then we don't need to teach it. If you don't know some of it, then it gives us a bit of an idea of what we might have for maybe future webinars, or just some interesting sort of info that we might share around as well.
Thank you, Sean. We'll talk about the poll results in a sec, but the questions have certainly come in thick and fast. So we're going to go through the people's questions that have put them in the Q&A, and if you put them in the chat, please put them in the Q&A if possible, because it makes it a lot easier for us to track. A lot of people are asking for can they get a copy of the recording and slides, and just remind, as I put in the chat, the recording and the slides will be made available on the Ocean Protect website under the webinars page in about a day or two. But look, I'm just going to run through the questions now. So Rowan B, who's been very patient from East Gippsland Shire, he asks, traffic calming alternative. I've seen these humps can block the major flow path. Are you aware of any alternatives to this?
No, really. When it comes to traffic calming, physical barriers are probably the most effective, I would think, because it's really going to constrain. Like if you've got a two-way road, I'm thinking of like typical urban low-speed areas. A lot of them you'll have two-way roads, and then you'll come and you have a bit of a blister or raised curb sort of profile, which chokes it down to one lane and a bit of a giveaway system or whatever. So if it's something like that I think you're talking about, if you just painted an island, just line marking on there, there's a good chance no one's going to follow that, and they'll just keep driving over the pavement. So having that physical raised island or blister or platform or whatever, it just forces you to have to move around, slow right down to squeeze through the gaps. So obviously that's how the traffic calming works. That absolutely affects the road capacity, or how much water can actually flow through there. You've got a very wide, shallow channel, and all of a sudden you're blocking half of that with a traffic island. So it absolutely will constrict it. And you have to check to see if that water can actually make its way through that, maybe reduce down to a single lane, for example. And a lot of the time it'll kind of split. You'll have a bit of curb flow, and then you have the rest of the flow that will get pushed around. There's nothing, there's no real way around it unless you wanted to, and I don't suggest this because this isn't practical, but the only way around it is to look at the approach flow and try to get that flow away somehow. How do you remove that approach flow? And so if it's already built and you're retrofitting a speed calming device, the only way to do it is put in a pit and then push some of that flow underground. But I don't suggest that because it's expensive, and you're only going to be able to capture small events. So I think it then comes back to just the road geometry, assessing how much flow is coming through, assess if the DV values are suitable, then it might be okay. The flows will just work around, but it's still acceptable. If you're designing a road from scratch, certainly they're the things that you've also got to design in as well, and you might be able to design out any issues before it comes to construction as well.
Cool. We are getting swamped with questions, and there's been a few questions around what to do when you've got an existing road. So I mentioned one of them. Let's go with Paul from GHD in Wellington, New Zealand. Paul asks, when renewing existing stormwater infrastructure, typically upsizing, we don't often have control over changing the road geometry too. Any advice for that situation, or should we all be convincing our local councils to agree to include road geometry design?
Yeah, very good question. A lot of the time you are stuck with the road geometry, especially when you've got residents all around. You can't just resume land and sort of build wider infrastructure or change the vertical geometry of the road. So yeah, you are stuck. I think the thing that I focus on in that sort of situations is just looking at a little bit larger, looking at the overall catchment to see what's actually happening. there's a lot of times where you're looking at the site and you're looking at a problem and you can't really figure a solution. But if you go a bit further, you'll actually see in the wider catchment, the catchment might behave in a certain way where there's a lot of flow coming from one area, and you might be able to do something upstream and actually divert the flow or capture it, and that will reduce the amount of approach flow that's impacting your particular site. A lot of the time, you're kind of stuck. You might have to increase the capacity of your underground drainage system. Now, that straight away raises concerns for me, because underground pit and pipe systems become blocked quite easily, especially when we get some pretty decent storms and you've got trees and stuff around as well. So when it comes to increasing the size of your infrastructure, definitely incorporate blockage factors, different scenarios, understand the maintenance behind it as well. Like, how often will these pits and pipes and roads be maintained? And be realistic. Don't be too optimistic. Like, if you know there are budget constraints or resource constraints, design for that, rather than just hope that it'll be perfectly cleaned out before that next storm. So yeah, agree with you. You can't do much with the road geometry. It really does come down to the increasing pit and pipe capacity, or just looking at the overall function of the catchment itself. And again, a lot of the time you can tweak that catchment upstream or in a few different ways, or divert maybe stormwater that's coming down into your system and surcharging. Maybe it's upstream, you divert that stormwater somewhere else, and you don't get as much water rising to the surface. But if you wanted to look at a particular area, please get in touch and we can always jump online and share screens and have a bit of a chat about what you could do.
Good stuff. Question from Sam Couch from City Gold Coast. Sam asks, could you explain the process you used to delineate the contributing catchment on the aerial image before applying Manning's equation? That step is often the hardest part to interpret.
Yes, absolutely. Catchment delineation is a bit of a it's a bit of a skill that you grow. You've got to draw thousands of catchments until you kind of get a feel for the topography. Essentially, and this, I think I cover a lot of this in those webinars as well, but if you're interested, again, give me an email and I can send you some information to go into a hell of a lot more detail when it comes to catchment delineation. But one of the first things that I'll do is look at basically aerial imagery. So you can jump on Google Maps and just have a bit of a look at that. Street view will help you understand the topography. You can get free LiDAR, bring that into your GIS system. So again, QGIS being free, you can bring that data in, and it's really just understanding the topography first. I'll talk for another hour if we go into catchment delineation, but a few things that you could definitely start. Draw in all your ridges, draw in all of your valleys, and that will kind of give you a bit of an idea where catchments will have, a bounding sort of area. And then once you've got a bit of a rough idea of those catchments, go out to site if possible and actually walk it and understand physically what's out there. You'll be surprised how many times what you think might happen, and then you go to site and all of a sudden there's like great big garden bed that's actually blocking a flow path, or impervious fences that are going right across a flow path. So that's probably a good starting point. But again, send an email through and we can obviously talk a lot more as well.
Another question from Ian McComb from Tasman District Council. Ian asks, do you have research on what V velocity is too much for surface stability, i.e. not having paving ripped off?
There's a bit of literature out there for surface. There's two things though. When you start looking at road, you got the road surface when the surface is just it's stable, and then you got water just running over the top. Now, normally for like an asphalt course, water's not really going to wear that away from the top. When it comes to like chip seal, then it's still pretty sort of stable. If you've got unsealed roads, so gravel roads, that's when you can start to look at scour. I'm trying to think of some values on top of my head, but there are certain values. But when it's sealed, you're probably okay. But the problem comes when you get water coming underneath, and it actually breaks the seal between call it the asphalt layer and your base course. If water gets under there, the hydrostatic pressure that can actually build up, depending on how that flood is sort of occurring, it's very easy to slip under, and all of a sudden your asphalt layer just peels off. It doesn't take much force from the stormwater to actually rip it off, and that's usually the main failure mechanism there. It's your asphalt and your base course. It loses that connection, and it basically just floats away. It just peels off, which is a pretty big issue. Aside from that, if you start looking at like, channel systems and you're looking at grass or vegetated systems or rock line systems, there's lots of different velocity sort of values that you use as well. And again, these are just numbers picked out of my brain. Don't troll me later on if I get them slightly out. But if you've got grass, you're looking at anything under a meter a second is pretty safe. Of course, there's dispersible soils you got to think about and everything else. If you've got just like dumped rock or placed rock, that's pretty good for 2, 3, 4, maybe 5 meters a second. After that, then you want to really make sure that whatever rock system you're using is actually locked in place. So it might be rock mattresses and gabion wire sort of structures, and that's good right up to maybe 8 meters a second or something. And then beyond that, you'd want to start looking at flow dissipators, actually busting up that flow, getting a bit of turbulence, and slow that velocity right down as well.
As a side note, one of my favorite stories around velocity and you mentioned velocity depth product. Do you know what the original study is based on, Sean? You probably do. 1973. 1973, University of New South Wales. They got 6 kids, I think ages like 5 to 11, without shoes, and they put them in a chute and adjusted the flow and the velocity and see what flow velocity depth took to wash them downstream. And that's still basically the basis of the VD limits. I know there was another study in 2003 by Yi, but I don't think the conclusion's changed. So engineers love their rules of thumb. It's amazing going back to seeing what they're actually based on. So can you imagine trying to get approval for that to wash some kids in a chute nowadays? So
you know what it was though? It'd be stormwater geeks like you and me, and you just throw your hand up. Yeah, I got my nephew can go do that.
Yeah,
or, my boy can go do that. Go in.
I reckon it was that. Anyway, well that's a side note. We'll dive in to more questions. Another one from Rowan from East Gippsland. He says some designers pond the road at the low point in the road, such as in the cul-de-sac, and use pit even for major flow. What ponding time is suitable or approved in QDM?
I would avoid that at all costs. The first thing that I look at, if you're doing pit and pipe design and you've got a sag pit, you need to look at what happens if that pit's completely blocked. Where does the overland flow path go? So there's, I still remember there was a job I worked on like years and years ago on the Gold Coast. I think it was Helensvale. There was a cul-de-sac. It came down. The cul-de-sac was right at the bottom. There was a sag pit at the bottom of the cul-de-sac itself, and then houses all around it. There was no overland flow path, so that pit could fill up, and basically as soon as it reached the verge level, it would break and then roll into people's driveways. Now, with any sort of subdivision like that, if you're designing it from scratch, what you would do is you would actually separate 2 of the houses at the lowest point and actually have a drainage reserve. Just council land, a few meters wide, shape it as a bit of a shallow channel. So if that cul-de-sac just filled up full of water, the pit wasn't doing what it needed to do, it could at least break and flow down your drainage reserve away from the houses. In this particular case, we didn't have that, or it wasn't our company to be honest, but like this one that we were investigating didn't have that. And so you had no option but to just capture all of that flow using that gully pit. So in that particular case, you'd want to make sure that gully pit is super over-designed to capture the major flow. And again, the biggest risk there, because we can design a pit that will actually take the major flow on paper in theory, but the biggest problem we have is blockage. And when you've got a sag pit, all of the rubbish and debris is going to flow down, and there's no velocity to sort of push it away. It's just going to sit there and then settle, and that's why it blocks so much, so easily or so quickly. Now for pondage time, there's not much written out there for pondage time for gully pits in cul-de-sacs, and I guess because you'd always want to make sure that it can at least free drain or break over. So if it was completely blocked, it'll just stay blocked until someone unblocks it. It really comes down to, I guess, nuisance, convenience, or in major storms, if it somehow is affecting evacuation, for whatever reason. I don't know what the scenario is, but if you had, say, a childcare, right next door, and then all of a sudden that ponding actually blocked the footpath, which was blocking people getting out of the childcare into a safer area, then you would really need to look at that duration and see what's deemed suitable, and you'd probably want that to be absolutely minimal. So yeah, interesting one. Again, if you wanted to, it's hard to kind of visualize, but if you ever wanted to talk in a bit more detail, we're always ready to share screens and crunch numbers and talk about the theory behind it. So definitely get in touch if you like. We can talk about it a bit more.
And look, we will be running out of time pretty soon, but there's still a bunch of questions. What I'm going to do, I'm going to sort of get, if Sean doesn't mind sticking around for a little bit longer, I'm going to run through the questions that we've got. And if there's others come through, we'll try and answer them. But just a reminder, folks, we've got another webinar in a couple of weeks, how to do buyer retention better, presented by yours truly, would you believe? I'm sure Sean will be coming along and asking a whole bunch of hard questions, but I'm gonna go back to the questions because they keep on charging through. Question from anonymous attendee. For blockage in pit and pipe design, do you assume blockage in both major and minor events or major only?
Yes, it's both major and minor events. It depends on the guideline that you're looking at. QDM, obviously I know that back to front. I've been reading that since day one that I started my career. In there, they talk about design events or design blockage factors, and then severe blockage factors. Design covers both minor and major, and they actually have the same value for either minor or major for that one. And then severe storms are when it's over and above your major event as a bit of a design check, if you like. But yes, you do need to incorporate blockage factors for minor events. It's not just major events. Yep.
There's quite a few questions around, I guess, varying geometry of the road. So if I use a question from, say, for example, Shayadol, they say a lot of road crossfall is not consistent along the road profile for old roads. For some instances, we see 15% crossfall. Road safe flow is compromised close to the lip line.
Yeah. If you want, send through an email and I can get in touch as well. But like that design spreadsheet that I had before is super handy. I might even just show you as an example. So the geometry itself is basically what you can punch in here. So you could take a existing road scenario, make multiple worksheets of this, and then you can really crank that crossfall right up, which will be your ZP value, which is somewhere here. So 1 in 40, you can go right up to say 1 in 10, even if you had like a 10% crossfall, and actually see how that works. But yes, it will affect your capacity quite a bit. When that is the case, definitely it's easiest just to crunch the numbers and just see what it looks like. The other beauty of having, and not just this spreadsheet, you can create your own as well if you like, but having something there to sort of look up, you can very quickly look at the different geometry of your road, but also different grades. So your road might actually, or most likely will change in longitudinal grade. So the crossfall and everything else might be pretty consistent, but the road goes really flat, then really steep, and then flat again. All of that's going to change, and you can't just say that a flatter road will give you worse outputs or a steep road will give you worse, because it's a depth velocity relationship that you're looking at. So really flat roads will have very low velocity, so that's great. It's slow moving, but it'll actually be quite deep. And then when you get really steep roads, you're going to have very shallow flow, but it's traveling very fast. And so it's, again, that balance that you'd have to look at.
Quite a few questions around flow widths, and I'll try and they're all asking more or less the same thing, I think. I'll pick Mika from Premise in New South Wales. Mika asks, why do councils need maximum 2 metre flow widths, and how much of the road profile can we use for the 1% AEP and still be within the Australian standards?
Good question. So the first one, the flow widths, it does depend on the minor and the major events that you're looking at. Obviously, minor events, it's quite frequent flow. So it's something that you're going to experience quite often. And so that's where it's more focused around convenience. So you, pardon me. So if you're driving through a road in a minor event, you don't want your road to have like 3 meters wider flow, and you're just always spraying water up everywhere, every summer, basically. So that's why you'd want to reduce those flow widths down. In major events, we know that it's going to be a lot less frequent. It's a rare event. So if there's a heap of water there, you've got to be a bit more careful, but it's not going to happen that often. The other thing you look at when you look at road flow widths is the type of road. Now, my subdivision, if I look outside now, really low speed environment, 40, 50 kilometer hour roads. It's just snaking around to get to people's homes. I don't mind if that floods, and the road flooded width is quite wide and it's a bit of a nuisance because there's not many people using that road. In those flood events, if I need to evacuate or if I need to get somewhere or, pick up kids from daycare because it's flooded, which I've done multiple times, I would want to make sure that those major roads, the arterial roads or the collector streets, I want to make sure that they are free from flooding. So your flooded width requirements will be a lot more stricter for those type of roads. And then your second part of the question, the major events, yes, it comes down to, obviously, you look at your DV values as well. That's probably the biggest governing factor. But also when it comes to the major event, you start looking at evacuation management and flood management sort of plans and scenarios. And again, depending on what type of road it is, or depending on whether it's access to a hospital or to a nearby school that might be used as shelters, they're the sort of things that start to come into play. And so it's not just your own little maybe subdivision that you're looking at. You might actually have to look at a bit bigger and see, well, how does this suburb or subdivision or residents, how do they actually escape if they need to, or get to critical sort of infrastructure or hospitals and that sort of thing as well. Yeah, a few things to think about. And again, if you want to talk it through and crunch numbers and jump online, just send me an email and we can organise that as well.
Cool. A couple of comments around pit inlet capacities. One person says, just mention pit inlet capacities, and another one asks, an anonymous attendee asks, what would be the best procedure for changing your design for a compliant velocity depth product? Adding more pits or increasing the lintel size?
Interesting. Both of them will kind of do a similar thing. So it's all about capture. How do you actually get the water from the surface and put it underground into the pipe system? So when we do any sort of pit and pipe design, we'll run through hydraulic capture charts. So for particular inlets. And so that's probably your first step. And you could very quickly compare the two, where you might have a 2.4 meter lintel, like a small lintel, and you can see how much approach flow and inflow will be captured if it's on grade, I'm guessing. And then you compare that with, say, a medium-sized lintel and a large-sized lintel, and just see how much extra water will actually be captured with that pit. So you could do that, and then you can compare with having a small lintel here and then maybe putting another small lintel, 40, 50 meters up the road and actually cutting off the approach flow. And you can do a similar calculation, say, well, if I do that, the flooded width's only going to reach, 2 meters upstream and then about 2 meters downstream. If I have one pit, but it's a large lintel, the flooded width might go right up to 3 meters and then finally get captured. And so then again, it's a bit of a balance. But yeah, really good question. Something that we cover when we do our pit pipe workshops as well. We'll crunch those numbers and we sort of let the team go away and do their own design and decide where they need to locate, different inlets as well. So yeah, very good question.
Question from Liesl Dingley from Chinchilla. Liesl asks, do the formulas discussed allow for changes to velocity down the roadside drain against the curb that occur once the depth becomes more significant, or does that not really happen in these types of settings as it doesn't get that deep?
It looks at basically what it's doing. You've got your curb and channel, and then you've got your pavement. And if you can imagine, not quite triangular, but they're kind of triangular shape. The curb's like this triangular bit of flow, and then the pavement's like a really wide but very shallow, again, kind of a triangular sort of a flow. And what the equation does is it basically looks at them in isolation, if you like, and then kind of combines the two. So it does take into account what the velocity would be based on a depth, I suppose, over your curb. That'll be slightly deeper than the depth over your pavement itself. So it incorporates those. It's almost like doing a Manning's check on the curb part and the pavement part and kind of adding them together. So yes, it does take into account. The velocity, though, it is the average normal velocity. So it's not talking about the velocity at the surface, at the water surface, or at the actual floor surface. It's a normalized average velocity for that one.
Cool. I see a comment from Chris Timini when we were talking about traffic calming. He's from Brisbane. Chris says, I've seen strip drains installed alongside the high side of a traffic island in Moreton Bay to prevent water ponding along the traffic calming device. I don't know if that cost would be accepted all the time, but it works well. And a question
Yes.
from Mark Lee from Sorrel Council, and he asks, existing roads with little or no stormwater infrastructure, where do you start?
Zoom out, look at the overall catchment. So you might have a road that you're maybe a bit concerned about. Actually go right out, and again, coming back to catchment delineation, work out how much catchment area is actually contributing to that particular road. How much upstream, how much downstream. You've got to look at the overall catchment, see how that's behaving first, and then you'll be able to start sort of picking and choosing problem areas and how to solve that. There's so many different scenarios and variables. That's the best bet, because you might be able to solve maybe some upstream issues or deviate flows in certain ways, and that might solve problems downstream. If you got a particular problem, again, reach out, send an email, and we can have a look and
I was going to
sort
say,
of talk about it as well.
where to start? Just call Sean, I think.
That's it. There we go.
The answer to all your problems. And look, we have gone over, but and thanks for everyone's time. Just for a couple of reminders, everyone asks the slides and the recording will be made available on that website. You can see there. Give us a day or two. And I'm sure there's some juicy nuggets that people want to revisit in the coming months. CPD forms, again, they'll be coming in your in-tray very, very shortly. Again, just a reminder, we've got a bunch of webinars to come in this year. So if you're keen to subscribe and attend, please do. Just jump on that website there to register or find out more. And how about just a very big thank you for Sean for giving up his time, sharing pearls of wisdom. He's a national treasure. Definitely in the running for Engineer of the Year in Queensland and Australia. If it's not too corrupted, we'll see. You've got to bribe a few more officials, I think, Sean. But look, it's certainly deserved. But we're certainly appreciative. And big thank you for everyone who's dialed in. And surely on behalf of everyone who's dialed in, I reckon they want to say Sean is a legend. So big thanks to Sean for his time. Looking forward to his subsequent webinars in the months to come. And we'll hopefully catch up in person sometime soon.
Excellent. Thanks, guys. Thanks for taking out the time too. It's always good to take out the time and learn something new and sort of, a bit of professional development as well. Grow and get a bit stronger as well. Thanks, Brad. As always.
No worries.
Catch you in the next one.
Enjoy the rest of your day, guys. Be good. Bye for now.